Now we're going to talk about the characterization of invertibility theorem. And so this is a big main idea, an underlying current that runs through the whole course, and we'll come back and touch on it again and expand on it. So characterization of invertibility. And it's sort of a neat collection of ideas, this theorem, because we see that the idea of understanding what it means to be for a matrix to be invertible has a bunch of very different aspects. So let's see. The following are equivalent. So I'll abbreviate this sometimes in future as TFAE. The following are equivalent. That means that each one of the following things is the same as all of the others. It's implied by it and it implies it. So the first one is A is invertible. And so this, by definition, this means that there exists a B with AB equals BA equals the identity. Okay, so that's the first one. Secondly, A is equal to a product of elementary matrices. So we've seen that if A is invertible, then it can be written as a product of elementary matrices, but it also goes the other way. If we have a product of elementary matrices, we know that each elementary matrix is invertible, and products of invertible matrices are invertible. So if A is a product of elementary matrices, then A must be invertible. So it's an if and only if. It goes back and forth, and that's the meaning of saying that it's that those two are equivalent. We've also seen that if A is invertible, then it can be row reduced to the identity. But if A is row equivalent to the identity, then we've seen that that means that it's a product of elementary matrices, because it's those elementary matrices that carry out the row operations that take the identity to A, or vice versa. So, and then along with that is sort of the twin version of that, which is that the reduced row echelon form of A is equal to the identity. Those two are clearly seen to be the same. We also have that AX equals B has a unique solution for any B. Okay, so it can always be solved. And so if A is invertible, then this is true, because we know that the solution is just obtained by multiplying B by A inverse. But it also goes the other way, so that if this system always has a unique solution, it can be shown that A has to be an invertible matrix. And then the last one is that if AX is equal to 0, so in other words, if X is a solution of the homogeneous equation, then it must be the case that X is the trivial solution. So in other words, this one's saying that the only solution of the homogeneous system is the trivial solution. Now, if A is invertible, then we know that AX equals B has a unique solution for any B, and in particular for 0. So AX equals 0 has a unique solution. And we know that 0 is always a solution of the homogeneous equation, so therefore it must be the only one. Okay, and so we're going to go back and forth between these ideas, forwards, backwards, sideways, up, down, whatever. Now, one thing that's doesn't, so and we're going to add to this theorem and include a bunch more points on there. One thing that's on here that's not on here yet is a nice criterion something that's nice and easy to compute to determine whether or not A is invertible. Now, you can row reduce and do all these things, etc., but it turns out that there's a way to determine whether or not A is invertible that typically requires less computation, or at least more efficient computations, and that is the determinant. So this is what we're going to be looking at in the next chapter. So the determinant of A is a number associated with A, and it's the notation for it is det A, or we put bars on it that look like absolute value bars. And the determinant tells whether or not A is invertible. It actually tells a lot more than that. Specifically, A is invertible if and only if the determinant of A is not equal to 0. But this criterion is one of the most important things about the determinant. So just as sort of like a final parting shot, we saw that only square matrices can be invertible. Rectangular non-square matrices don't have a hope. And similarly, determinants only exist for square matrices.